तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will move on to a newer topic that is computing Fourier transforms using numerical methods. So we are all familiar with Fourier series, that is when you have a function which is periodic in time. So let us say this such a function, some function which is periodic in time or any variable t, and it is periodic in the sense that okay, now it has a repeat period of given by t here, and let us say this continues, and then we know that such a function can be written as a sum of sine functions and sine and cos function, that is a n sine some, we will say some n omega t plus sigma n b n cos n omega t. So we can write, we know this is the Fourier series when this function is periodic, and where omega here would be 2 pi by t. So we can write this in this form, and then we know that to obtain the coefficients a n and b n, we would integrate this function f of t. Right. So we would say that to get a n, we would say that we will integrate this function between the limits minus t by 2 to plus t by 2, f of t, we will say sine n omega t dt. So that's what we would do to obtain this coefficients, right. So because we use the property of the sine functions that integral minus pi to plus pi sine n omega t sine m omega t dt is equal to pi times delta n m. That is what we are familiar with. So this means that this is non-zero only when n equal to m, right, and when it is n equal to m, the value is pi. So we can use this property and obtain these coefficients as a n as f of t sine n omega t dt and b n as f of t cos n omega t dt. This is something which we are familiar with in the Fourier series, and we always say that the function has to be periodic for you to obtain to be able, for that you can write it in this form. So Fourier transforms is the extension of this into even non-periodic functions. Okay. So that is what we are going to look at that here. Okay. So remember that what we did here was to write the function as a sum of sine and cosine functions with some coefficients a and bn, and then we would obtain the coefficients a and bn by integrating, multiplying this function with sine and cos respectively and integrating from minus t by 2 to plus t by 2. So, it is a 1 over t of minus t by 2 to plus t by 2 is what you will get that this. Okay, so that is something which we are all familiar with. So, now let us say we have, instead of a periodic function like this, let us say we have a function of this form. Let us say we have a function which is something like this. Okay, so, we have a function t and f of t. Okay. So, we have a finite set of coefficients. We will get, when you have this periodic function, we have a finite set of coefficients. You will find this, okay, a n and b n, okay, which would make up this periodic function, which repeats itself. On the other hand, if you have a blip like this, okay, and then you will have, if you want to write this in terms of sine and cosine function, there will be there will be infinite number of harmonics in this kind of a function. Okay. So, the extension of the Fourier series, okay, Fourier series to functions of this form, okay, the extension of the Fourier series to functions of this form would be to write this as f of omega as integral minus infinity to plus infinity e to the power of I omega t f of t dt. So, that would be the form. Okay, actually you should write I omega here, f of I omega as, so normally written with a capital F. Okay, so, f of I omega as minus infinity to plus infinity of e to the power of I omega t f of t dt. And so, this function are called the Fourier transform of f of t for some variable t. So, for some variable t I can write an integral of this form, okay, e to the power of I omega t f of t dt, and then I would get f of omega. So, that is the extension of the Fourier series which we know of for non-periodic functions. Okay, so, for non-periodic functions, instead of writing a Fourier series, we would write a Fourier transform, and the Fourier transform is given by this. Okay. And the inverse Fourier transform would be then, well, we can also write f of t in terms of f of omega, and then we would write 1 over 2 pi integral minus infinity to plus infinity. Now, e to the power of minus I omega t f of I omega. So, now we write f of I omega d omega. Okay, so, that would be the inverse Fourier transform. Okay. So, now we have a definition of a Fourier transform and an inverse Fourier transform. So, what we would be concerned about is how to compute such quantities when we have a discrete set of data points, when we have the function itself sampled at a discrete set of points in t, and then how do we compute the transform of such functions, and that is what we would be concerned about here. That is to say that we have values of the function given at, let us say, some discrete interval t by n, well, let t is the total interval we have. So, we have a finite set of discrete values, okay, that collected let us say in an interval from 0 to capital T, that is the total interval which we have, okay, and then let us say it is in n equally spaced sub intervals. We have this data collected, that is equal space delta t is t by n, okay, and then how do we compute the Fourier transform of this. So, that's we will, such computation would be called a discrete Fourier transform, as opposed to the integral transform. We will use a discrete Fourier transform. So, we, as opposed to an integral to obtain the Fourier transform, we will here do a discrete sum, okay, and that is what we will be looking at. So, to fix the notation, we with the data collected, let us say f of t is our sample, the data collected in this interval we will write as f subscript n. Okay, so, that is the data f at time t is at time t f as a function of t collected at the interval at nth interval will be written as f n, and that is what we would be using it. Okay, so remember this thing. So, what we have to do is to do a Fourier analysis of a non periodic function of this form. Okay. So, that is what we want to do. So, and then we would write that Fourier transform and the inverse transform in this fashion. This 1 by 2 pi could be in either of them, but not in both, or if you can, or you could put either here or here. So, this is that part of the definition. Okay, this 2 pi, which is kind of normalizing factor here. So, that is what we are trying to compute. So, now we let us say we do not have the data a continuous form like this, but we have it collected at equal intervals, okay, in this variable t, okay, which let us say in the interval from 0 to t, and then we want to do the transform of that and then compute the transform of that. That is what we will be now looking at. So, the discrete Fourier transform, when we compute, as I said that we would divide the interval into n equally spaced subintervals and denote the function by fn. So, graphically it does that you have a function which goes from 0 to t, and then you sample this at equal intervals here, and then each of this values in each of this values we denote by fn. So, that is the idea. Okay. And then this transform, which is our continuous transform, that is e minus infinity to plus infinity, f of t e to the power of I omega t dt, which is now sampled at n equal intervals. So, we define this notation omega k here, which I read, as 2 pi by n times some integer k. So, this transform is then written as in this form. Okay. So, we would write the discrete transform from the continuous one, that is f of k. So, this what we have written before as f of I omega k equal to integral minus infinity to plus infinity f of t e to the power of I omega k t dt will now be written as a sum of all the function values f n. Remember, n is the function value sampled at the nth interval, multiplied by e to the power of minus I omega naught k times n. So, where k and n here are integers, and the sum goes from n equal to 0 to n minus 1. Okay. There are n points here. So, n goes from 0 to n minus 1. So, this 1 by n is again is a normalizing factors, which can be put either in this or in the inverse Fourier transform. So, this continuous transform is then now turned into a discrete sum, and the inverse transform, which is f of I omega k e to the power of I omega k t d omega k for every t, is now written as f n as k going from 0 to n minus 1 f k e to the power of I omega 0 k n. So, remember, k and n are integers here. So, now this is equivalent of saying f of t is equal to integral minus infinity to plus infinity f of I omega k e to the power of I omega k t d omega k. So, remember, omega k here is 2 pi by n times k, where k is an integer. Okay. So, now this is the two expressions which we are going to use to compute the discrete Fourier transform. Okay. So, that is the Fourier transform. This is a function evaluated at a discrete set of points, and then we would get the f of k's, okay, and using the f of k's we can compute the function at that discrete set of points using the inverse Fourier transform. So this is the two transforms, and now you can see that if I want to actually compute this transform using this n functions, okay, n intervals, okay, and then to compute this quantity for every k we have to do n into n operations. Okay, so let's look at that. So this has to be computed. So we have n values of f, right, capital N values of f from 0 to f n minus 1. Okay, so this sum now that we know what the discrete transform is, now this sum is to for every k going from 0 to n minus 1. Okay, so there are n such k's. Okay, now for each of this case we have to do n sums. Okay, so n products and n sums. So the number of operations goes as n squared. So as you increase the k, okay, number of k values or the number of n values, okay, the computation involves also blows up as n squared. And similarly for the inverse Fourier transform. So that's the problem with computing the discrete Fourier transform. Okay, so you can compute this. Okay, so one way of computing this is the following, that we use the property that this can be written as a cos, that is if I can write fk as 1 over n, okay, so times sigma n going from 0 to k minus 1, then we say that it is fn times cos of cos of omega 0 kn plus I times sine of omega 0 kn. Okay, so that's how we compute this. Okay, so we have to evaluate these functions at all the, for each k we have to evaluate these functions n times, okay, and then do this product separately. We write it in this fashion so that even in languages like C, which cannot handle complex numbers, this is a complex number, so languages like C which cannot handle complex numbers can do this transform, can compute this transform by using doing it in two different parts. So we have imagine if we have a f of k is real part, so we'll compute fk real. Okay, so real part of f of k, let's call it as fk real. Okay, so that will be 1 over n sigma n equal to 0 to k minus 1 fn cos of omega 0 kn. Okay, and then we compute f k imaginary part as 1 over n sigma n equal to 0 to k minus 1 fn sine of omega 0 kn. So we can compute these two separately and thus don't have to handle a complex number. But the problem is really that the number of operations are extremely high. So that's the problem with this discrete Fourier transform computation of discrete Fourier transform. Okay, so there are better methods of doing this, and one of them is called the fast Fourier transform, and that's what we would be actually interested in. So let me just summarize this. So we would divide the interval t into n equal intervals, okay, and then denote the functions by fn, okay, and then you would compute the Fourier transform as using this form, that is e to the power of I k omega 0 n fn as the Fourier transform, and the inverse Fourier transform as 1 over n sigma n equal to 0 to sorry here it should be k equal to 0 to n minus 1, okay, e to the power of the sum is over k and the sum is over n. So where omega 0 here is some 2 pi by n. Because as I said, the problem is the number of operations here, okay, and the number of operations can be reduced while going to what is called a fast Fourier transform. Okay, so this DFT, which is discrete Fourier transform, requires n squared complex operations, or the complex operations can be reduced to the real operations by writing this as e to the power of cos I k omega 0 n plus I sin k omega 0 n, and then computing the real and imaginary part separately. That means we actually have 2 times n square real operations in this computation. So one way to go around this is to use what is called a fast Fourier transform. This is a very clever technique which allows us to compute this discrete Fourier transform in n log n operations. So we use the symmetry of the trigonometric functions to get to compute this discrete Fourier transform in n log n operations. Okay, so that's what we would be now looking at. Okay, so the basic idea is here that you have this n with n number, n functions. Okay, we have n functions. Okay, now this n is now we have n such intervals. Okay, let's write that here. Okay, so we would let's say we have functions like f0, f1, f2, f3, f4, f5, f6 and f7. Okay, let's say we have 8 such functions values. Okay, and then the idea is that we would divide this into 0 to 3 1 and 4 to 7 1 and compute the discrete Fourier transform of each of them. Okay, and then we can show that the whole idea behind discrete fast Fourier transform is that we can actually divide this into smaller and smaller subsets and then compute the Fourier transform as a cascade. Okay, that's what we would see. Okay, so that's the whole idea because what's called the Sande-Tukey algorithm. So we'll see that now in the. So the algorithm is the following, that we would write the Fourier transform fk of the function fn, okay, as a function of this form, okay, that is sigma n going to 0 to n minus 1 fn w n k. Okay, so now that's same as this what we have written here. Okay, so this one. Okay, now the w and now the n k is nothing but that. Okay, so we are going to write this function here. Okay, so as this discrete Fourier transform we are going to write as let's forget 1 over n for the time being. Okay, so let's say this is our discrete Fourier transform. We'll put the 1 over n in the inverse Fourier transform, okay, and then we write this as sigma n going from 0 to capital N minus 1. We'll say that it is fn, and we say some function we call w, okay, to the power kn. K and n are integers. So now this w is nothing but e to the power of minus I omega naught. Okay, and remember omega naught is 2 pi by n. Okay, that's what we have here. So now this is the form which we are going to write. So now remember we will always be using this w. So this w is e to the power of minus I omega naught, and I would write this as this transform as fn e w times kn. Okay, so now as I said we will divide this interval into 2. So this interval n minus 1, this n in the n functions will now divide it to n by 2 and n by 2 and write this sum now sigma n going from 0 to n by 2 minus 1 fn w kn plus sigma n going from n by 2 to n minus 1 fn w kn. Okay, so that's what we would write. Okay, let's use slightly different. Okay, it doesn't matter. Okay, so we have sigma n going to 0 to n by 2 minus 1. So this n is now split into So the n functions are now n function values which we have is split into now two intervals. One goes from 0 to n by 2 minus 1 and other goes from n by 2 to n minus 1. So these two intervals we will write. Okay, so now we will make a small change of variable so that the sum is actually going from 0 to n by 2 minus 1. Okay, so we want to write that. Okay, so the way we can write that is to say that this is sigma n equal to 0 to n by 2 minus 1 fn w kn w to the power kn, and then we say that here in the sigma we say this is f n, we call some variable m plus n by 2 at w power km. Okay, now the m now goes from 0 to n by 2 minus 1. So m goes from 0 to n by 2 minus 1. Okay, so you see when m is 0, this is n by 2, and that's what when n is n by 2, that's what we have. So these two are the same, right? I just made a small change of variable, went from n to m, so and then by adding, so as n is actually m plus n by 2. So I made n is m plus n by 2. So I made this small change of variable to write this as this both the sum as 0 to n by 2 minus 1. So I can sorry, here also I had to write that n by 2. Okay, so I have this thing here. So now you see these are dummy variables, m and n are dummy variables, so I can just write them as n itself. So I will write the Fourier transform, my discrete Fourier transform now as n going to 0 to n by 2 minus 1. I will say fn w kn plus fn w power k times n plus capital N by 2. Okay. So now you see my sum is now only over n by 2 function values. Okay, and one, so this fn w, so what I have done is this is a dummy variable, so I just write the sum. I just took this line is exactly the same as this line, only thing is I put the sum as 1 here because m and n are dummy variables. Okay, so I can actually pull out fn from here, and you can see, so you can write, sorry, I can pull out wkn from here. Okay, and then write this sum as the fn plus n by 2 w to the power n by 2 multiplied by wkn. Okay, so let's write it that fashion. Okay, so going back from here, we would write, so now what we have written is this, that the Fourier transform we wrote as f k as sigma n equal to 0 to capital N minus 1, and we said I can write as fn w kn plus sigma m going from n by 2 to capital N minus 1. Okay, this is n by 2 minus 1, this is n minus 1. We said I can write it as fn w kn. I just split that into 2, this Fourier sum, and then we made a change of variable, and then we got this now as sigma n going from 0 to n by 2 minus 1. I can write it as fn plus w to the power k n by 2 into f n plus capital N by 2 into w k n. Okay, so what we have done is to make a change of variable here, right, and then I wrote it as m going from 0 to n by 2 minus 1, right. So by making a change of variable, so this will become fn plus m by 2, and w to the power of k n plus m by 2, right, and then we split that. So let us go through over this again once again. So we have this written here, and then I made a change of variable here, and then make this going from, instead of going from n by 2 to n minus 1, I have it going from m going to 0 to n by 2 minus 1, okay, and then I change this to m plus n by 2, and here also m plus n by 2. Basically I made this change of variable here, and then I said that this n and m are dummy variables, so I can pull that out, okay, and write it as fn both as sum over n, okay. So nothing which prevents me from doing that because it is dummy variables, and then I can pull out this omega kn from this. Omega kn I can pull out, it's common in both the terms, and write it as fn plus wkn by 2 fn plus n by 2 wkn. So now remember what's w. So w was nothing but e to the power of minus I times 2 pi by n. That was our w, that is I omega naught was 2 pi by n. So it is I times minus I times 2 pi by n. So what is w to the power kn? So w to the power kn by 2. So w to the power kn by 2 is nothing but e to the power of minus I 2 pi by n into k times n by 2, right. Okay, so that is, we know, is nothing but e to the power of minus I pi to the power k. So the realizing this is the key to fast Fourier transform. Okay. So from up to this, it's still a discrete Fourier transform. All we have done was to split this into two halves, okay, and we are still doing the same number of sums. Okay, so here again we are doing the same number of sums, but now we realize that this w to the power of k n by 2 is actually e to the power of minus I pi to the power k, and we know that e to the power of I pi is just minus 1. Okay. So this is just minus 1, so what we have here is actually minus 1 to the power k. Here, now that's a trick. Right. So we have minus 1 to the power k. So all we have to do is to write this as now fn plus minus 1 to the power k fn plus n by 2. Now this is obvious that this would mean that for all odd integers this becomes minus, and for all even k's it becomes plus. So if you are computing fk for even k's, okay, then this is fn plus fn by 2, and if it's for odd k's then we are computing it as fn minus fn minus by 2. Okay, so that's the sum. So we will write this sum now. Remember this. So we can write this as minus 1 to the power. So that is nothing but minus 1 to the power k. Okay, so we have now this fk as, so we say fk as sigma n going from 0 to n by 2 minus 1. We say fn plus fn plus n by 2 wkn for k odd, for odd k, right, and equal to sigma n going from 0 to n by 2 minus 1 fn minus fn plus n by 2 wkn for even k. Okay, sorry, minus for even k plus for minus for odd k and plus for even k. So we have this sums. Okay, we now have two different functions. We have the sum of the functions here for all the even k values, and difference between the functions in the two halves for the odd k values. Okay, so remember, if you have the function tabulated in this form, okay, so now that is taking the difference between two functions for all the odd k values, and taking the sum between the functions, so this and that. So we divide this into two halves here. Okay. So what we are going to do is we are taking the difference between these two and the sum between these two. So this is 0 and n by 2 minus 1, right. So that's what we are going to do. So we are going to take the sum and the difference between these half functions and this half functions and write them. Okay, so that's the key to this Sande-Tukey algorithm. Okay. So let me summarize this again here. So we write this function fk as fn wnk, and then we would write that as two different sums that goes from 0 to n by 2 minus 1 and n by 2 to n minus 1, right, two functions fn e to the power of minus I. This is my omega naught which I have written here as kn, and e to the power of minus I 2 pi by n kn. So now these can be written by just small change of variable from going from this again the second part. Okay, as we said, the second part here, we make a small change of variable here and make this sum go from same 0 to n by 2 minus 1. That I can do by defining a variable m, which is n minus n by 2. So that's what I have done here. So we have that here. So we have m going from 0 to n by 2 minus 1 f m plus n by 2 e to the power of I. Now there is even this m has to be replaced by m plus n by 2. So this part. So the second part of the sum which modified a little bit and to this form. So that the sum is going from 0 to n by 2 minus 1 here, and it going from 0 to n by 2 minus 1 here also. So I could pull out this sum here and also pull out this e to the power of 2 pi minus I 2 pi by n kn, which is common for both of this because m is just a dummy variable. Okay, so I can pull out these two and then write it as fn e to the power of minus I pi k now. Okay, because pi k, because now when I multiply it here, you see this 2 pi by n, then this n by 2 cancels, so we have I pi k. So fn plus e to the power of minus I pi k fn plus n by 2 e to the power of minus 2 pi kn by n. So that's our Fourier transform, and then we said that now this is nothing but minus 1 to the power k. Okay, so that things become simple. So I can write now this as two different parts. Okay, so I can write this as two different parts. One is for the even values, that is f2k's. Okay, so now I can write for the even functions, I write it as sum, right, because minus 1 to the power k is 1 for even k values, so that is f2k. If I can write it as for k going from 0 to n by 2, right, so I can write it as f2k, and then for all the even functions I have it as a sum of these two, and for the odd functions that is 2k plus 1. So I split this sum k into 2k and 2k plus 1. Okay, so then I can write that as the difference between these two functions. So I have two things quantities here. So I have a f2k and a plus and a minus function here. Okay, so we have 2k plus 1. Okay, so the idea here is that I am writing this as for odd k values this one and even k values this. So to make sure that it is odds, I would write this as 2k. I can change that, okay, and 2k, and then say that this is for all k going from 0 to n by 2, right, n by 2. I can do this for n minus 1 2. Okay, I can do this for all k values for 2k. So I can do this up to that n by 2 minus 1, sorry, n by 2 minus 2 here it will be. So I will have that many values in the even thing, and similarly I can write this as f2k plus 1. Okay, so for this, sorry, again 2k and 2k plus 1. This is for the odd functions and this is for the even values. Okay, I can write this as two different sums. One for two, this is to make sure that this is 2k. So I should write here also as 2k. And I should write here as 2k plus n times n. Okay. So I have two sums here. Okay. One is 2k plus 1, other is over 2k. So that's for odd and the even functions. So that's what's here. So this is for the odd function. Okay. So w to the power 2k plus 1 is now here split into two parts. One is 2 pi n by n, another is 2 pi k n by n by 2. So two parts are just, this is basically just w to the power 2k plus 1. Okay, so that's for the odd values. For the even values, remember it is a sum here. So now that's the basic algorithm. Okay, now this algorithm now can be implemented. Okay, so in these two sums, okay, can be implemented very in an easy fashion by replacing the function values by its sum and its difference. Okay, now that's a whole trick here. So we have this f2k, that's for the, we have a series of fn function values. Okay, we have going from 0 to n by, we have 0 to n, right. So we have 0 to n minus 1. So we have n function values. Now this n function values we take, okay, and we split that into two halves, okay, n by 2 minus 1 and n by 2 to n. And then what we do is we take the sum and difference of these functions values and replace these functions by its sum and difference. Okay, so we will use the same array and then replace them by the same sum and difference. So that's what you are going to do. Okay, so you see that we wanted to compute for the odd and the even values of k. So one is replaced by the sum and other is replaced by the difference, and then we do the discrete Fourier transform of that. So if you look at this expression here, these two expressions, you see this very clearly that this is the expression for the discrete Fourier transform of n by 2 functions, n by 2 function values, right, which is given by fn plus fn n by 2, right, and this is our normal Fourier transform. So remember how did we write the discrete Fourier transform? So when we wrote the discrete Fourier transform, we said that fk is sigma n going from 0 to n by 2 minus 1 fn plus fn e to the power of I omega k. So that's the same thing here, I omega k, that's what we written. So now here the function to whose discrete Fourier transform we want to find is now fn plus n by 2, that's the sum of the two functions here. And here the second part is the discrete Fourier transform of the difference of these two functions. Okay, so let me say that again. So following that we have this function values here. Okay, so now what we do is we take the sum, let's say. Okay, now I'll write f0 plus f4 here, okay, and this and that. Okay, I take the sum, okay, and I write that. Okay, and I take the difference and I write that here, f0 minus f4, and also multiplied by w to the power, in this case it will be w to the power n. Okay, so that's what we have to write here. And then because you see the difference here is that for the even functions it is w to the power 2nk, and of the odd functions we have the difference, and there is also this extra wn here. Okay, so I would have to write that also when I do the sum. Okay, fine. So I would write this also here, w to the power n. And similarly I could take for all of them. Okay, now this will be replaced by f1 plus f5, and this will be by f2 plus f6, and this will be f3 by f3 plus f7. Again, all the differences we would write here, that is f1 minus f5 and f2 minus f6 and f3 minus f7, okay, all of them multiplied by wn. Okay, and then we can do the discrete Fourier transform of each of them. Okay, now you do the discrete Fourier transform of each of these values, okay, each of these function sets, okay, and then we would get the desired answer. But now you see, we know that the scaling, let us look at the scaling. We said that the discrete Fourier transform as n squared operations. Okay, so we have n is equal to 8 here, so we will have about 64 operations here. Okay, and then while this is 4 and this is 4, okay, so then we will have 16 plus 16 operations. Okay, so we have 32 operations. So by splitting this into two halves, okay, and then doing the discrete Fourier transform of each of them, okay, we are able to reduce the number of operations. Okay, now we can split this into further. Okay, we can split this again further here, okay, and do the discrete Fourier transform for each of them. And that's the idea of the fast Fourier transform. Okay. So graphically, we can show that here. So okay, so before that, let me just summarize this. So what we are saying is we are defining new functions, which is fn plus n by 2 and fn minus fn by 2. Basically, this is what I am calling. These functions would be called now as G0. So let me call this. In the notation we use, this is G0, G1, G2, G3, and this we would call as H0, H1, H0, H1, H2 and H3. Okay, and we do the discrete Fourier transform for each of these functions here separately, and that's what is written here. Okay, now these Fourier transforms would be called Gk and Hk. Okay, so this is, remember now it's 2nk here. Okay, so it's 2nk. So when you're multiplying, when you do the discrete Fourier transform, remember that this would be 2nk, where omega, where w here is e to the power of I times 2 pi by capital N into 2nk here. And if you're doing the whole function Fourier transform, discrete Fourier transform, you would be writing it as fn. So remember, it will be, if it's a full Fourier transform using discrete Fourier transform, then we would be saying that fk here will be equal to sigma n equal to 0 to n minus 1. Right? This n is actually n by 2. It's some reduced to half. Okay, so otherwise it will be n minus 1 gn w n k. This is gk function. So we have actually reduced the numbers into two halves here. Okay, so now that can be, I can show this in a simple graphically. I will show this in this fashion. So I have this f0, f1, f2, f3, f4, f5, f6, f7 listed here. Then you take two functions f0 and f4, right, and make the sum and the difference, and you write the sum here and the difference here. Okay, and then you could do this for all the function values. Okay, so you do that for f0, f4, f1, f5, f2, f6, etc., and then you get these two sets. Okay, and now this is what we call G0, G1, G2, G3, and this we will call H0, H1, H2, H3. Okay, and then you do an n by 2 point discrete Fourier transform here. Okay, and then the n by 2 point discrete Fourier transform would give us the Fourier transform of all the k values which are even here and all the odd values here. Okay, so let me repeat this again. That is, I take these function values, I tabulate them here. Okay, and then I take the sum. Okay, so for example f0 and f4, so this is the line which marks that. Okay, f0 and f4. Okay, and I take the sum here and write that. Yeah. And then I take the difference between that f0 and f4, which is here, that's the difference, multiply it by w0, w to the power 0. So because I have written here, remember I have to multiply it by this n. Okay, so n here is the 0, so w0, and then in this case it will be w1, and in this case it will be w2, and in this case it will be w squared and w cube, etc. So that's what we have to write, and that's what I've written here. So here, so let's replay this once again. You have these functions here, okay, and you take these two, right, and then you find the difference is written here and the sum there, okay, and similarly you find all the sums and differences for each of the pairs, right? And then you take these functions here, the differences, multiply them by the weight, that is w to the power 0, w to the power 1, w2 and w3, and then tabulate them as G0, G1, G2, G3 and H0, H1, H2 and H3. And then you have a set of n by 2 points here, and you have another set of n by 2 points here, and you do the discrete Fourier transform of that. Let's say we stop it here. We can actually do this again. So we continue this operation, but let's look at this. Okay, I can do a n by 2 point discrete Fourier transform here. Now what you get is here the f, okay, of the Fourier transform of this. If this whole thing was a black box, we didn't know what's going on. We put in these functions here, and we got the Fourier transforms out here. But when you put in f0, okay, you get the corresponding Fourier transform capital F0, right? And you put in f7 and you get the corresponding Fourier transform f7. This is k equal to 7 and this is for k equal to 0. But where the f1 will now be replaced by f2, and f2 will be replaced by f4 and f3 by f6. Okay, so now it's not so when you put in here the function values, if it's into this black box, you put in the function values in this order, the Fourier transform we get in a slightly jumbled up order. Okay, so we are going to get it as f0, f0, and then we are going to get f2 either k equal to 2, k equal to 4, k equal to 6, and then k equal to 1, 3, 5 and 7, because we have segregated the even and the odd Fourier transforms. So now we can do this, continue this again, right? We can take this box here, okay, which has now n by 2 points, in this case it has 4 points, okay, and this 4 points can be split further up. So we see that to start with we had this 8 points, and then we made them into groups of 4, right, and then we did a 4-point DFT here. So as I said, we will further divide this 4 points and then continue this process. Okay, so let's look at that in the next slide. So we have here this 8 points, so that's 0 to 7, and then you had this. Now we had then grouped them into 4 and 4, and then we said that we could do a 4-point Fourier transform here. So let's do a 4-point fast Fourier transform again here. Okay. So that's, we could do a 4-point discrete Fourier transform, or we could do a 4-point fast Fourier transform. So let's do this fast Fourier transform here. So that means we'll again do what we did on this points here again. That's, we took this 4 and 4 and we added f0 to f4 and replaced f0 with that sum, and we took the difference between f0 and f4 and replaced f4 with that difference multiplied by w to the power 0, and we took f1, the difference between the sum of f1 and f5, and replaced f1 with that sum, and we took the difference between f1 and f5 and multiplied by w to the power 1 and replaced f5 with that, and so on. So we'll do exactly the same here. So now the input to this was, remember, is G0, G1. Let's just go back and then see that again. So we have the input as G0, G1, G2, G3, and here the input we call as H0, H1, H2 and H3. So when we do a n by 2 point fast Fourier transform instead of DFT, we will take G0 and G2, find the sum, replace G0 with that, okay, and then G1 and G3 and take the sum and replace G1 with that, and then take the difference between G0 and G2 and multiply it by w to the power 0 and replace G2 with that, and take the difference between G1 and G3, multiply it by w to the power 2 and replace G3 with that. So notice that difference, that is when we did take the difference here, we go over by w0, w1, w2, w squared, w3, etc., right. But when we do that here, that we take G0 minus G2 multiplied by w to the power 0, while G0 minus G3 multiplied by w to the power 2. Okay. And similarly here we replace H2 by H0 minus H2 into w to the power 0 and H1 minus H3 into w to the power 2. That is what we do. Okay. So when we do that, okay, what we get is starting from this values, okay, so we will get n, we have this n by 2 points, and we do this g0, g1, g2, g3 here, and h0, h1, h2 here, and then we do again a Fourier transform here, okay, fast Fourier transform by doing the split. So let us look at that here. Okay, so now that's the 4 points, have g0, g1, g2 and g3, right, and then we can take the sum and the difference of g0 and g2, right, and replace g0 and g2 by the sum and the difference. Okay, so again, so note that when I multiply g2 and g3 with w's, it is w0 and w2, w squared, okay, w2 I mean w squared. Okay. So when then now we have this set of 2 points here and the set of 2 points here, right. Now I can again do the continue this transform again by taking these 2 points and then these 2 points as 2 different set. So we had 8 which is split into 4, and then that's further split into 2 each, and then that 2 we'll use and take the sum and difference and write now the whatever we got here. Okay, so now we take that the sum of these 2 and replace this point with the sum, and take the difference between these 2 multiplied by w to the power 0, which and replace, that is just the difference, and then you replace this point with that. Okay, similarly we take the sum between these 2 points and replace this point with the sum, and take the difference and replace this point with the difference. So now that gives us the Fourier transforms. Okay, so final answer when you do this cascading. Okay, similarly we can do for h also, right. So we could do the same thing for h. Okay, so we have the h0, h1, h2, h3 here. Okay, we take the sum between h0 and h2, okay, and replace h0 with that. Okay, take the difference between h0 and h2 and then replace h2 with that, and take the sum between h1 and h3 and replace h1 with that sum, and take the difference between h1 and h3 multiplied by w to the power 2 and replace h3 with that. And now we take these two points, take the sum, replace the first point with that, and take the difference, replace the second point with that, and similarly here. So that leads to the full Fourier transform, and you do that here. Okay, so the end result is that we have the Fourier transforms, okay, and in this order. Okay, so when we do this thing, it's as we are taking the sum and the difference and replacing those numbers with those sum and the difference multiplied by the appropriate weights. Okay, what we find is that we actually jumble up the order of the Fourier transform. Okay. So we start with an array which contains the function values at 0 in an array which is from, say, let's say in this case dimension from 0 to 7. Okay, and in this case, and finally what we get is the Fourier transforms, which are again goes from 0 to 7, but not in the same order as which we got here. Okay, so it's not in the same order that we get here. Okay, so there is the highest value and the lowest value will be the same for the k values, so f0 and f7, but the in between values get jumbled up. You can see that after f0, the next array point, that is what we had the function in the f1, is now replaced by the Fourier transform for k equal to 4. Okay, and f2 is say the same as 2, but f3 is now replaced by the Fourier transform at k equal to 6. So what we see is that we start with an array which contain function values from 0 to 7. Okay, we started with that, and then we are ending with Fourier transforms of in the same array. The same array, the functions are now replaced by its Fourier transforms, but not in the same order. Okay, so now what order it comes in, and how we can decipher which k value of which function value is replaced by the Fourier transform is for what k values are they replaced for. We will see that in the next class.